So we'll work some problems out of section 9.2 and 9.3. In the 9.1 we dealt with sequences. Now we're going to be looking at series, and a series is taking terms of a sequence and adding them all the way to infinity. So this is different than just a regular sum. These sums actually let n go all the way to infinity. So list or find the first 5 terms of the sequence of partial sums. S2, S sub 3, S sub 4, and S sub 5. Where S sub 1 is the very first one, where we put a 1 in, and we get negative 1 to the 1 plus 1 over 1 factorial. So negative 1 squared is 1, 1 factorial is 1. So we get 1 for the very first term. So the first partial sum is just the first term. The second partial sum is the first term, which is 1, plus the second term. If we plug a 2 in, we get negative 1 to the 2 plus 1 over 2 factorial. So 1, negative 1 cubed is negative 1. 2 factorial is 2. So 1 minus 1/2, or 1/2. So that's the sum of the first 2 terms. This is the first term. That's the second term. That's putting them together. So when we put the first 2 terms together, we get 1/2. And then the third term, if we put a 3 in, we have negative 1 to the 3 plus 1 over 3 factorial. So 1/2, negative 1 to the 4th is positive 1. 3 factorial is 6. So 1/2 plus 1/6, which we could get a common denominator. That'd be 3/6 plus 1/6, which is 4/6, or 2/3. So that's adding the first 3 terms together. The fourth partial sum takes adding the first 4 terms together. So 2/3 plus the next term. The next term is negative 1 to the 4 plus 1 over 4 factorial. So 2/3. Negative 1 to the 5th is minus 1. 4 factorial is 6 times 4, or 24. The common denominator will be 24, so we get 16 24ths minus 1 24th. So 15 24ths, or 5/8. So that's the fourth partial sum. The fifth partial sum is 4 terms plus the 5th term. So negative 1 to the 5 plus 1 over 5 factorial. So negative 1 to the 6 is positive 1. 5 factorial, this was 6. This was 24. 24 times 5 is 120. We'll get a common denominator there, which will be 120, I believe. 120 divided by 8 is 15. So we need to multiply 8 times 15 to make that a 120 on bottom. So that'll make that a 75 over 120. Let's see, that reduces. 4 goes into both of those. Make sure I type that correctly, and that's right. 4 goes into the top 19 times. 4 goes into the bottom 30 times. So that's the first term, the sum of the first 2, the sum of the first 3, 4, and then 5. So those are our first 5 partial sums. So this one wants us to find what this series converges to, and then I believe it may also ask for several different partial sums. If we just begin listing individual terms, when we put a 1 in, we get 6 over 1 times 4. If we put a 2 in, we get 6 over 2 times 5. And then we get 6 over 3 times 6. And we get 6 over 4 times 7. And so forth. And we could add those together. And if we do it in this format, it's going to be hard to get a particular pattern. So one thing that we can notice is we have two terms in the denominator, or two factors, not two terms. And bottom, we can rewrite this as something over n and something over n plus 3. So if we put these together, we would have a n plus 3 over n times n plus 3. And we would have bn over n times n plus 3, just rewriting each of those fractions with our common denominator. So 6 over n times n plus 3 will equal a times n plus 3 plus b times n over the common denominator. So since the denominators match, the numerators have to match. Just like we did in the last chapter, we can pick very specific numbers for n in order to find a and b. For example, if we let n equal 0, then this term would be 0, so we would get 6 equals a times 3, so a is 2. If we let n equal negative 3, then this term would be 0, and we would get 6 equals negative 3b, or b equals negative 2. That means our series can be rewritten. Instead of 6 over n times n plus 3, we could call it 2 over n minus 2 over n plus 3. So we list our first several terms in this series. If we put in a 1 minus 2 over 4. And then if we put in a 2, we get 2 over 2 minus 2 over 5. And then put in a 3, we get 2/3 minus 2/6. And then we get 2/4 minus 2/7. And then, let's see, that was 1, 2, 3, 4. If we put a 5, we get 2 over 5 minus 2 over 8. And let's do one more. 2 over 6 minus 2 over 9. And since we're going to infinity, that just keeps on going forever. But let's notice some things. First, second, third, fourth, fifth, sixth. After a while, we start having some terms that are replicated and they have their opposites. Notice we have a minus 2/4 here, we have a positive 2/4 here. So once we add past the third term, that one and that one cancel. We have a minus 2/5 here, we're going to have a positive 2/5 here. We have a minus 2/6 here, we have a positive 2/6 there. We have a minus 2/7 here, our next term would have a positive 2/7. So those are going to cancel. So after a while, we're going to be left with a 2 out front. That one's never going to have, there's never going to be a minus 2 over 1. Minus 2 over 4 is the smallest one we have. There's never going to be a minus 2 over 2. And there's not going to be a minus 2 over 3. So we're going to have all of those. Now we just need a way of describing what we have left. So when we use this 2 over 6, and that to cancel that one, that was our sixth partial sum. That was adding the first 6 together. So for our we're going to be left with a 2, a 1, a 2/3, and then we have a minus 2/7 that's going to go away, a minus 2/8 that's going to go away, and a minus 2/9. Let's list the next term. Our seventh partial sum, we would be adding a 2 over 7 and a minus 2 over 10. Our seventh partial sum, our minus 2/7 and plus 2/7 would go away. So we'd have the 2, the 1, the 2/3. The 2/7 would be gone now, and we'd be left with a minus 2/8, the minus 2/9, and a minus 2 over 10. If we put another term in, if we do the 8th term, we have 2 over 8 minus 2 over 11. So this time, the minus 2 over 8 and the plus 2 over 8 cancel. So for our 8th partial sum, we have our 2, our 1, our 2/3, and we're left with a minus 2 over 9, a minus 2 over 10, and a minus 2 over 11. So with these three, we should be able to pick up a pattern. All of these have a 2, a 1, and a 2/3, and then we have three terms that we're subtracting. This denominator is 1 more than n. This denominator is 1 more than n, and so is this one. So 1 more than n would be n plus 1. This one is 2 more than n, so n plus 2, and that one is 3 more. So this formula gives us our nth partial sum. If we want to find out what do we get when we add our first 100 terms together, we would have a 2 plus 1, that's 3, plus 2/3, we could call that 3 and 2/3. Then we'd have a minus 2 over 100 plus 1, a minus 2 over 100 plus 2, and a minus 2 over 100 plus 3. So that would be adding the first 100 together. Now notice these terms are getting closer and closer and closer to 0. So our sum of our series is what happens when we let our nth partial sum when we let n go to infinity. So if we look at our formula here, if we let n go to infinity, we keep the 2. The limit of any constant is a constant. We keep the 1 and we keep the 2/3. But the limit of each of those go to 0. If n goes to infinity, each of those go to 0. So 3 and 2/3, or we could call that 11/3, is what that particular sum goes to. So that's this telescoping series converges. This is what it converges to, but we do need this formula in case we need to find the value of certain partial sums. Then we're asked to find the sum of this convergence series. This particular one is a geometric series. There are several in this section that are geometric series. And the way a geometric series is constructed is to get from one term to the next, we're multiplying by the same ratio each time. So for example, if we started with 2, and then the next term is 2/3, and the next term is 2/9, and the next term is 2 over 27, to get from this term to that one, we're multiplying by 1/3. To get from here to here, we're multiplying by 1/3. From here to here times 1/3. So if we're multiplying by the same ratio each time to get the next number in the sequence, this is a geometric series. The first term is known as A. R is the ratio that we're multiplying by each time. And this converges as long as the absolute value of R is between 0 and 1. Think about if R is between 0 and 1, then we're multiplying by a fraction that's going to make us get smaller and smaller. If we multiply by 1, we keep the same number each time. If we multiply by something bigger than 1, our number is getting bigger each time. But here, since we're multiplying by a number that's smaller than 1, then our number is going to be getting smaller. So as our infinite series gets more and more terms, what we're adding is getting smaller and smaller and smaller. So even though we might be accumulating, the amount we accumulate each time is a smaller and smaller and smaller amount. A classic example of a geometric series is this problem. If we look at this square, if we call it a 1 by 1 square, then it has an area of 1. If we take it and cut it in half, it still has an area of 1. This side has an area of 1/2, and this is 1/2. If we cut this one in half, if we take half of a half, then this one is a fourth, and this one is a fourth. If we take half of this one, then this one is an eighth, and that's an eighth. Cut it again, this would be a 16th. This would be a 32nd. This would be a 64th. A 1 over 28. And we can keep on doing that forever and ever and ever and ever. So we're adding more and more each time, but what is that total area going to be when we add all of those rectangles together? That total area is going to be 1. So that is a series where we're taking 1/2 to the n power, and we're adding those up. So when n is 1, we have 1/2. When n is 2, we have 1/4. When n is 3, we have 1/8, then 1/16, then 1/32, on forever. So this is a visual representation of that series, and visually we see that that series converges to a total of 1. This is A, and to get from one term in the sequence to the next term, each time we're multiplying by 1/2, so R is 1/2. So as long as R, the absolute value of R, is between 0 and 1, it's going to converge. And it converges to A over 1 minus R. So this down here, this was just another example. So if we list some terms in this sequence, notice they let n start at 0, which is kind of normal for a geometric series. If we put a 0 in, anything to the 0 power is 1. Then if we put in a 1, we get minus 4 over 9. Then we get 16 over 81. Then we get minus 64 over, was 81 times 9? That's 729. So forth. So to get from one term to the next, one term to the next, we're multiplying by negative 4 over 9 each time. The way we recognize this is if we have a constant to a variable power. A constant to a variable power. And the absolute value of that is less than 1. It's between 0 and 1. So this one is going to converge. And define what it converges to, we use the formula A over 1 minus R. So A over 1 minus R is negative 4/9. So to get a common denominator, it would be 9. So 9 over 9. 2 negatives make a positive. So on bottom, we end up with 13 over 9. If we divide by a fraction, we multiply by its reciprocal. So when we add that convergent series together, the terms will make their way towards 9 over 13. If we were to list more and more partial sums of this geometric series, as the terms if we get more and more terms, infinite number of terms, this is what we approach. Okay, here's another one. Terms or fractions, let's put a 1 under the first term. They say find the sum of the convergent series. They don't tell us what kind of series it is to begin with, but let's see if we can pick up a pattern. Notice each numerator is 3 to a power. To get from here to here, we're multiplying by 3. Here to here times 3 times 3. And each denominator is a power of 4. So from here to here, we're multiplying by 4, and then times another 4, and times another 4. So we're multiplying by 3 on top, 4 on bottom each time. Our first term is 3. So this is a geometric series. It's geometric because to get from one term to the next, we're multiplying by the same number on top and bottom each time, by the same fraction. So since the absolute value of that is between 0 and 1, it converges, which they tell us that it's convergent, and it converges to a over 1 minus r, so 3 over 1 minus 3/4. 1 minus 3/4 is 1/4. If we're dividing by 1/4, we're really multiplying by 4. So that converges, adds up to 12. If we add more and more and more terms to that, that approaches 12. This one, if we just list some terms of it, it says start with n equal 2. So 2 over natural log of 2. And then 3 over natural log of 3. And then 4 over natural log of 4. If we notice, there's not a number that we can multiply, that we're multiplying by each time to generate the numerator. We're not multiplying by the same number. We're not increasing at a constant ratio. We're just increasing by one number each time. We're adding, not multiplying. So this one is not geometric. It's also not telescoping because we don't have one term minus another term. So if it's not geometric or telescoping, then to find out if it's convergent or divergent, then we have a list of tests, different things we're going to look for. So we have some series generated by a sequence, and we're going to call that a sub n. If a sub n, if it does not go to 0 as n goes to infinity, then our series diverges. What do I mean by that? In order for this to converge, then as time goes by, our terms have to be getting smaller and smaller and smaller, and not just smaller, they have to be getting closer to 0. Even if they're getting smaller, but they're approaching a number like, let's say, 1, then eventually we would be adding 1 or close to 1 forever and ever and ever. And if we're adding a number that's close to 1 forever and ever, then that's going to be getting bigger and bigger and bigger towards infinity, and it's going to diverge. The only way this could possibly converge is if after enough time each term is basically 0. If each term is basically 0 and we're just adding 0 forever and ever and ever, then it's possible that that converges. There are still some cases where that diverges, but that is possible to converge. So let's check to see if it's even possible for this to converge. If this sequence doesn't go to 0, we know it diverges. So let's find out. Let's take the limit as n goes to infinity of our sequence that generates our series. By direct substitution, we have infinity over infinity. Natural log of infinity is just infinite. So that's the determinant. So we can use L'Hopital's rule. Take the derivative of the top and then the derivative of the bottom. Dividing by 1 over n is like multiplying by n over 1. So that is just n. Well, as n goes to infinity, that expression goes to infinity, which means we diverge. These are getting bigger and bigger and bigger and bigger. And if we're adding numbers that are getting bigger and bigger and bigger, then our partial sums are getting larger and larger and larger, and they're going towards infinity. If they're going towards infinity, then they diverge. They don't go to a specific number. Okay, so let's see if the integral series, or if the integral test can be applied to this series. So we have to meet some constraints. Our function has to be positive. It has to be continuous. And it has to be decreasing. There are some examples where maybe the first couple terms are not decreasing, but once it gets past a couple terms, it has to decrease forever. So our sequence, e to the negative n, we can compare that with the function f of x equals e to the negative x. The sequence and the function are the same at integer values. The function corresponds to more values than just integer x's, where the sequence only applies when n is an integer. So they should have some similar characteristics. So first of all, is it positive? E to the negative x can also be written as 1 over e to the x. E is a positive number. We're looking for values where n goes to infinity. Likewise, x would go from 1 to infinity. If e is a positive number and x is going to be a positive exponent, a positive number raised to any power is positive. Positive over positive will be positive. So it's always positive. Also, this is always going to be continuous. E to the x cannot equal 0. If we try to take natural log of both sides to find out, well, when would e to the x equal 0, we can't take natural log of 0. That's undefined. So there is no value that will make it discontinuous, so by default it is continuous. The derivative of our function is minus e to the negative x, or we could call that negative 1 over e to the x. This part in parentheses, we've already demonstrated that that's always positive. A negative times a positive is negative. So regardless of what x is, this is always going to be negative. If our first derivative is negative, that means we're decreasing. So we're decreasing for every value of x that we have. So it's always decreasing. So if we meet those criteria, then we can use the integral test to determine whether or not our series converges or diverges. Real quickly, if we look at our sequence, it's positive, and over time it's getting smaller, smaller, and smaller, and smaller. If we compare that to our function is a continuous line. That red line or red curve represents the function. If if we think about drawing rectangles that are 1 inch or 1 unit wide, so we don't start at 0, we start at 1. So if we go 1, 2, 3, 4, 5, 6, 7, each of those rectangles is 1 unit wide. Delta x is 1. So the area of that rectangle would just be given by the corresponding y value. F of 2, f of 3, f of 4, f of 5. Because when we multiply it times the width, anything times 1 is itself. So we could approximate the area by just adding f of 1 plus f of 2 plus f of 3 plus f of 4 and so forth. So really what we're doing is these are the values of the sequence. When we're approximating the area underneath that curve with those rectangles, we're really just getting the sum for our series. Now, it's not, sometimes this is going to converge, sometimes it's going to diverge. Sometimes when we find the exact area, not the approximated, but the exact area underneath this curve, remember from the last chapter, sometimes when we did an improper integral, sometimes it diverged. It turns out if this area diverges, then the series itself diverges. But if this area converges, then the series converges. Because we have this relationship between the series, which is essentially the area approximation using rectangle, 1 unit wide. So, the integral, and see what we get. So since it's an improper integral, we're going to rewrite this as the limit as b goes to infinity of the integral from 1 to b e to the negative x dx. So this looks like an e to the u du. So if u is negative x, du would be negative 1 dx. So put a negative there and a negative there. So we have negative the integral of e to the u du, which integrates into e to the u with a minus out front. So this integral, negative e to the u du, integrates into negative e to the u. We're evaluating that from 1 to b, goes to infinity. So if we put in a b, we get minus e to the negative b. And then if we put in a 1, we get minus e to the negative 1. Right? If we let b go to infinity, if this exponent goes to infinity, then that's like having 1 over e to the infinity. Negative infinity, we could move to the denominator, call that positive infinity. If the numerator is constant and the denominator goes to infinity, that goes to 0. So we have 0 minus a negative makes it positive, e to the negative 1, or we can call that 1 over e. So that means our integral converges. Our integral converges to that. So if our integral converges, then so does our series. It also converges. But if our integral would have diverged, then our series would also have diverged. All right. Let's take a look at this one. We want to look at a series that goes from, I believe, 1 to infinity. And this is our series. This is the first term, second term, third term, fourth term, fifth term. And we're using 1 over 2n plus 8 for our formula. In that replicate each other. This just is in terms of x, that's in terms of n. Remember, n goes from 1 to infinity, and n is an integer. X goes from 1 to infinity, but it can be any real number. 1 to infinity. So let's see, first of all, can we use the integral test here? So is this positive? Is it continuous? And is it decreasing? Well, this is going to always be positive because the numerator is positive and 2n plus 8 is always positive if n is 1 or bigger. If n is 1, we get 8. If n is 2, we get 12. If n is 3, we get 14. So for all n's that are positive, that's going to work. So it's always positive. That's only continuous when that's only discontinuous when the denominator is 0, which is when n equals -4. But -4 is not inside the counters that we're using. Our counter starts at 1. So it's continuous. And then we just need to see, is it decreasing? So if we take 2n, or we could say 2x plus 8 to the -1 power, if we take the derivative of that, we'd have to use the chain rule, so bring your exponent down, times the derivative of the inside, or we could call that -2 over 2x plus 8 squared. That's our derivative. The numerator is always negative. The denominator, since it's squared, is always positive. So that's always going to be negative. So since our first derivative is always negative, it's always decreasing. So we meet our qualifications to do the integral test. So to do the integral test, we want to of the integral that goes from 1 to b of 1 over 2x plus 8 dx. If we let the denominator be u, then du is 2 dx. So we need a 2 here. So we have up front. This is just du over u. Du over u integrates into natural log absolute value of u, which our u is 2x plus 8. And we evaluate that from 1 to b. So we have 1/2 natural log, put in a b, we get 2b plus 8. Minus 1/2 natural log, put in a 1. 2 times 1 plus 8. We get that answer. And if you notice this term, when b goes to infinity, we're taking natural log of infinity, which is infinitely big. That's a constant, but an infinity minus a constant still goes to infinity. So our integral diverged. Integral diverges, then our sequence also diverges. So if the integral diverges, the series also diverges. All right. Here again, they ask us whether we can use the integral test for this one. This is always going to be positive. If n is a positive number, the denominator is always positive. The top is always positive. So it's positive. It's continuous because n starts at 1. So the denominator is never going to be undefined. And if n is 1 or bigger, the numerator is not going to be undefined. So it's continuous. And then we can show it's decreasing. We can take the derivative and show whether or not it's always decreasing. So if we let f of x be natural log of x over x to the 5th, we would have to use the quotient rule to take the derivative. So the derivative of the top times the bottom minus the top times the derivative of the bottom excuse me, over the denominator squared. So we get x to the 4th. That's actually a common factor because we have x to the 4th there and x to the 4th there. So we can pull an x to the 4th out. That leaves us a 1 for the first term, a 5 times natural log x for the second term, x to the 10th on bottom. That reduces. So our first derivative is 1 minus 5 natural log x over x to the 6th. Now, to begin with, when x is 1, log of 1 is 0, so we would get 1 over 1 that is positive. But it's not going to take very long before the numerator is going to be negative. Any number to the 6th power is going to be positive because 6 is an even number, so we're going to have positive on bottom. And real shortly, for any value of x, probably from 2 to infinity, those are all going to be negative on top. So this is going to be from 1 to infinity, natural log of x over x to the 5th dx. And we would find out, does that diverge or does that converge? For time's sake, we're not going to do that integral right now, but I'll just give you a hint. You could do that integration by parts. There may be a formula for that in the table also. But since it's improper, we would rewrite it as a limit. And as I said, we could integrate that by parts, find out what that integral is, evaluate it, and take the limit. And then we would see, does that converge or does that diverge? Now, the last type of series that we have in this section is what's known as a p-series. So p-series, or special series, p-series are series that can be written in the form 1 over n to the p. P or power series. The base is our counter, and the power is a constant. So let's look at 1 over n to the 4. We can use the integral test to evaluate that. If we compare that to the integral 1 to infinity of 1 over x dx, then dx over x integrates into natural log absolute value of x. If we evaluate that from 1 to infinity, which technically we take the limit as we go close to infinity, Well, natural log of infinity is infinitely large, so that one diverges. That diverges. But if we compare it to, let's say, 1 over x squared, when x is 2, we could also call that x to the negative 2. That integrates as x to the 1 bigger power over that power. That's evaluated from 1 to infinity. Technically, we take the limit, but we're just kind of doing this quickly just to illustrate. So if we put an infinity in, we have negative 1 over infinity to the negative 1, or infinity to the positive 1 on bottom. And if we put a 1 in, we get a 1 there. If the denominator is going to infinity, that's going to 0. Those cancel, so we get a constant, so we're converging. If this is a 3, if that's a 3, then we would have x to the 1 greater power over that power, so we would have an x squared on bottom. If we have an x squared on bottom and we're going to infinity, that still goes to 0. That still, as long as when we go towards infinity, that goes to 0, and that's a constant, then we converge. So if p is, when it's 1, it diverged. But if p is greater than 1, we're going to converge. It could even be 1.1. As long as our power is more than 1, we're going to converge. But if we're 1 or less, notice our power here is 1, then we diverge. So let's see if we can take this one, and I'm just going to copy it to another page. And try to illustrate that it is a p-series, and then determine based on the power we converge or diverge. So notice we have a 2 underneath the radical. 32 power. Notice we have a 3 under the radical. 343 is 3 to the 5th power. You do 3 raised to the 5th power, that's 243. 4 under the radical there. 1024 is 4 to the 5th. 4 to the 5th. And this last one is 5 to the 5th. Square roots of 5. So if we look at our successive terms, we have 2 to the 5th, square root of 2, if we're multiplying, we add the exponent. 5 plus 1. So 2, 5 or 11/2 power. Here, our base is 3. Our exponent is again 5 plus 1/2. Then our base is 4. 5 plus 1/2 is our exponent, and then 5. So our series n starts at 1, goes to infinity, and we have 1 over n to the 11/2. That's our series. So this is a p-series because our base is our counter. We can call this 1 over 1 to the 11/2 because 1 to any power is 1. 1 over 1 is 1. So it's our counter to the 11/2. Our counter to the 11/2. So p-series, our exponent on bottom is our p. And since that's greater than 1, then our p-series converges. If we were to add these terms on forever and ever and ever, we would converge to a particular number. We don't know what we're converging to, we just know that we converge.